All right, today we're going to begin another technique for figuring out integrals, and this is known as the technique of partial fractions, also sometimes called partial fraction decomposition. And the thing about partial fractions is it's actually a technique that's really an algebra technique. It's not even really a calculus technique, but it's useful in calculus. And the reason is because what if I wanted to do an integral like this? I think the best way to do this is to just show you an integral and see what we can do with it. So let's suppose that I have something like 2x plus 1 divided by x squared plus 5x plus 6 dx. Now, we could probably do this integral using the techniques that we've come up with so far. Okay, what we could do is we could complete the square on the bottom, and then we could look at the result, and either maybe this would come out to be something we can do by using trig substitution. We might get lucky and part of it might turn into an arctangent or something like this, because remember, often when you have like x squared plus 1 in the denominator, fractions like that, often we can deal with those using inverse trig functions. Remember, go back and look at the derivatives of inverse trig functions. They come out to stuff like this. But it would be very messy and difficult to do it that way. We would eventually get through it. But what if there were an easier way? What if there were a better way of approaching this problem that involved maybe less work? Or what if this problem were more complicated and those options weren't there? Here is the idea. Let us suppose that I want to try to rewrite this fraction. Now, you can do this partial fraction technique as long as the numerator has a smaller degree than the denominator. So we will address what do you do if the numerator has a larger degree in a little bit, but or if they're the same degree, then we'll deal with that in a minute. But as long as the numerator has a smaller degree than the denominator, here's what we can do. We'll factor the denominator, and we will rewrite this as 2x plus 1 over x plus 2 times x plus 3. That's what we're really trying to integrate. And the idea behind partial fractions is if I just have a bunch of separate linear factors like this, then I can try asking, well, how would I make this fraction as a sum of fractions whose denominators are going to be x plus 2 and x plus 3? Well, let's just put some constants up top here for the moment, and then let's see if we can find constants that will make this equation true. If we can do that, then I can turn the original integral into an integral of these two things. And notice that if I could do that, this would become an almost trivial integration problem because the antiderivatives of a constant over a linear expression, that's just a logarithm of some kind. So that's going to actually be very, very easy. Now, how do we figure this out? Well, here's the way we do it. We'll multiply both sides by this denominator on the left, and we get 2x plus 1 is equal to a. Now, the x plus 2's cancel and leave me with a times x plus 3, and then I get b times x plus 2, because over here, the x plus 3's cancel. So I'm just multiplying both sides by this denominator here to get to this step. Now, at this point, there are two different approaches that we can take. One of them is we can say this means 2x plus 1 is equal to a plus b times x plus 3a plus 2b. And then we can say, well, this means that a plus b is equal to 2 and 3a plus 2b is equal to 1. And because of that, we get this system of equations. We can solve them for a and b. The reason I can do this is because if two polynomials are equal, the only way that can happen is if the coefficients of the polynomials are equal. So that is what we are going for here. Now, there's a slightly easier trick in this particular case that we can use. And it comes back to the fact that we know what would make some of these things 0. So instead of going through this process, which would be frankly perfectly fine, we could get through it. But I want to show you a shortcut trick. Instead of having to deal with this system of equations, what if we just evaluated these polynomials at certain numbers? The reason that that's going to be so convenient here is because we know what will make these terms 0. If I plug in -3, I get 2 times -3 plus 1 equals a times -3 plus 3 plus b times -3, plus 2. And now this term with a goes to 0, and I am left with, let's see, 2 times -3, that's -6, plus 1, that gives me -5. On the right-hand side, I get -5 equals -b, or b is equal to 5. And then, if I plugged in -2 here, I can do exactly the same trick. Because plugging in -2 will get rid of the term involving b. So I would get 2 times -2 plus 1 is equal to a times -2 plus 3. And again, you see that if I plug in -2 here for x, the term with b's goes away. So this is going to give me -3 is equal to a. So I have figured out that I can drop my eraser and then catch it. And this becomes -3 over x plus 2, and then 5 over x plus 3. So now, this original integral is going to become the integral of -3 over x plus 2 plus 5 over x plus 3 dx. And as I say, this is quite easy to do. This is just going to be -3 log absolute value of x plus 2 plus 5 log absolute value of x plus 3. And of course, if we wanted to, we could go ahead and we could combine these logarithms into one by like using the rules for logarithms, right? So this is actually going to be the natural log of the absolute value of x plus 3 to the 5th divided by the absolute value of x plus 2 to the 3rd. But like, do we even want to bother with that? I don't know. It kind of depends on the situation. Maybe we want to do that. Maybe we don't. I don't really care, honestly. Just whatever you want to do is fine. Your homeworks may ask you to simplify it into this form for some of the problems, so it's good to be able to do that, but it's not something that I would say is super essential to be able to do. Or rather, it's essential that you know how to do it, but I wouldn't say that in every problem you always want to put it in this form. Depending upon what we want to do next, quite honestly, this form might be easier to work with. So this is the idea of partial fractions. Now, as I said, you could probably have done this example with some other tricks as well, but I think you'd find that they would be more difficult. And here is an example that I have conveniently written down where we wouldn't be able to do this. So what if I wanted to do the integral of 3x squared minus 5x plus 2 divided by x cubed minus 5x squared plus 6x dx. We cannot do this by the other methods that we've done so far. I always hesitate to say you can't do it because maybe eventually you'd find some weird trick that will work. But I don't see a way, honestly, of doing this using trig substitution or any of the other stuff that we've done so far. So if you want to mess around with it and see if you can figure something out that would eventually work, feel free. But I am not holding my breath on figuring anything out. But here's what I can do. I can rewrite this as the integral of 3x squared minus 5x plus 2. If I factor the denominator, this becomes x times x minus 2 times x minus 3. And that is what we are integrating. So what I'm going to do now is I'm going to set up this equation, 3x squared minus 5x plus 2 divided by x times x minus 2 times x minus 3. I'm going to set this equal to a over x. I'm going to try to make my x more readable. Then I'm going to have b over x minus 2. And finally, I'm going to have c over x minus 3. So for each factor in the denominator, I need to put a separate fraction here. And then what I want to do is I just want to try to do the same thing as we did last time. So we're going to have 3x squared minus 5x plus 2 is equal to a times x minus 2 times x minus 3 plus b times x minus 3 plus c times x minus 2. Once again, I just multiplied through by the denominator on both sides, and that's given me this. Now, you could expand this out and compare the coefficients. In fact, earlier I tried doing that, and it's certainly possible, but it's kind of annoying, and when I tried doing it, I ended up making a mistake where I lost a minus sign, and it screwed me up for a while, and it was really a pain. So the easier thing to do is let's plug in some values here and see if we can choose values in a smart way that is going to help us to find what these values are. So what could I plug in that would get rid of the b and the c terms and just leave me with a? Take a moment to think about that. Well, the answer is I could plug in a 0 because the b term and the c term, they both have they both have x as a factor. The a term does not. So if I plug in 0, I would get 2 is equal to a times 0 minus 2 times 0 minus 3, and that would give me 2 equals 6a, or a is equal to 1 over 3. Now, take a minute and see if you can find b and c by doing the same methods. And I want you to actually pause this and take a minute to think about this problem and see if you can figure it out for yourself. All right, so let's go through and let's try to work through this example together now, figure out what b and c are by using the same kind of methods. What would I plug in order to just have the b term? Well, if I plug in positive 2, that would get rid of the a term and the c term. So we plug in 2, that would give me 3 times 2 squared minus 5 times 2 plus 2 is equal to b times 2 minus 3. So that would give me, I'm running out of space on this little tiny whiteboard here, but that would give me, let's see, this is going to be 12 minus 10 plus 2. So that gives me 4. And then on the right-hand side, I'm going to have negative 2b. Hold on, did it actually come out that nicely? I didn't think it came out quite this nicely when I looked at this before. Let me just quickly double check to make sure that I haven't, done something weird again. Okay, sorry, yes, I double checked and this is indeed correct. I was confusing myself with what I had in my notes from before. So b is equal to negative 2 here. And finally, we want to go through and find c. Well, what can I plug in to find c? I'm going to plug in positive 3 here because that gets rid of all of those other terms. So I get 3 times 3 squared minus 5 times 3 plus 2 is equal to c times 3 times 3 minus 2. So this is going to give me 27 minus 15, that's 12, plus 2 is 14, and on the right-hand side, I'm going to have 3c. So this gives me c equals 14 over 3. And this is going to allow me to rewrite this original thing, this original integral, in terms of these fractions. So my integral is actually going to be the integral of 1 over 3x minus 2 over x minus 2 plus 14 over 3 times x minus 3 dx. And now, what we've gotten to at this point is another one of these problems where you can just go ahead and each one of these terms, you integrate it and you get a nice logarithm. So there we go. Everything is great so far in this problem. And I'll leave it to you guys to figure out the actual logarithms that you get. But it's, like I said, everything at this point is a nice straightforward integral. So we wouldn't have been able to do this at all if we had been trying to do it just directly from this original thing. We would have been really stuck. I mean, maybe somebody comes up with a trick where I can do this by a trick substitution, but I don't think so. I don't think it would be, it definitely wouldn't be easy. There's nothing obvious to me here, and I don't even think it's possible. But with the method of partial fractions, although the partial fraction method itself is a little bit complicated or lengthy, it's just a little bit of algebra to work this out, and it turns it into a fairly simple integral here. So let me write down the basic rules for partial fractions here that we can say so far. If we have p of x over q of x, where the degree of p is strictly less than the degree of q, and also we can factor q into q of x is equal to some overall constant times x minus c1, x minus c2, all the way out to x minus cn, then all we have to do is we write p of x over q of x is equal to a over x minus c1 plus b over x minus c2 all the way out to, well, maybe we should call it a1 and then a2 all the way out to an divided by x minus cn. So if the denominator factors into a bunch of linear factors, then you can always break up the integral this way. As long as none of these factors are repeated. So as long as all the ci's are different. And that's a really important point, that they do have to be different. If you get a repeated factor, then that makes things a little bit more complicated, although it's still not too bad. But we'll deal with what do you do if you get a repeated factor later. Now, what do you do if the numerator is a larger degree than your denominator? Well, here's the nice thing. We can always write, and this is something you may remember from your pre-calculus course, though you probably haven't seen it since then. For any polynomials p of x over q of x, we can always write this as capital Q of x plus p of x divided, not p of x, r of x divided by q of x, where the degree of r is less than the degree of q. In other words, every rational function is a polynomial plus a rational function where the numerator is smaller than the denominator. And how do we do this? Well, we do it by using polynomial division. So let me very quickly remind you, how do you do this polynomial division so that you can then use partial fractions. And to give you an example of this kind of thing, let's suppose that I need to do the integral of 4x cubed minus 6x squared plus 2 divided by x squared, let's just say x squared minus 1. Because I don't want to do anything super complicated here for this example. I want to show you one that's this will give you the idea, and then you can work in the slightly more complicated examples as you go. So what would I do? I cannot just apply partial fractions because the numerator is a larger degree than the denominator. So what I do is I do polynomial division. And let me write this up here. I have 4x cubed minus 6x squared plus 0x plus 2. It is being divided by x squared minus 1. To get the 4x cubed, I would need to multiply by a 4x squared. That gives me 4x cubed minus 4x squared. And now I take the difference. The difference, minus 4x squared. Sorry, I would multiply by a 4x here. That would leave me with 4x cubed minus 4x. And when I take the difference, that leaves me with negative 6x squared plus 4x plus 2. To get the negative 6x squared, I would need to multiply by a minus 6, and that would give me minus 6x squared plus 6x. And when I take the difference, this leaves me with negative 2x plus 2. So, what I can do is I can rewrite my original integral as the integral of 4x minus 6 plus negative 2x plus 2 divided by x squared minus 1 dx. Because all I've done is I've rewritten this rational expression in terms of a quotient polynomial plus a remainder polynomial over the divisor polynomial. And now I'm in a situation where the first part of this integral is one that we can take care of just by integrating the polynomial. And the last part of this integral we can do by partial fractions. How would I do this by partial fractions? Well, I can break up negative 2x plus 2 divided by x plus 1 times x minus 1. And I can break this up using partial fractions. I can set this equal to a over x plus 1 plus b over x minus 1. And now we're pretty much in the same scenario as we've been in the previous examples. So I will leave it for you to kind of finish out this and see where this ends up. But at this point, we've gotten everything into a place where we can do these antiderivatives. Once again, you might actually think, oh, well, I could actually do this by doing a trig substitution. Yeah, you could, but frankly, I would much rather do partial fractions like this and get it in terms of logarithms than try to do some trig substitution stuff. Whichever way you want to do it is fine. You'll get a correct answer either way. The other thing, though, is I don't actually know, when you do trig substitution on this, you might end up with something really ugly that's difficult to integrate. So I wouldn't guarantee that trig substitution is going to work here. I mean, you would need to do x is equal to secant theta, so you'd end up with like a secant over a tangent. Yeah, it'd probably work, but let's not mess around with it. Let's just do it by partial fractions if we can. Now, what if you have repeated linear factors? That is going to give you a bit of a problem. And the thing that you need to remember if you have linear factors is that we need to add in some extra terms. Oh, excuse me for just 1 second. Okay, so I think the easiest way to explain this is with an example. Let's suppose that I have x squared plus, let me make sure I'm doing the right thing here, plus x plus 1 divided by, let's say, x cubed plus 3x squared plus 3x plus 1. Now, the nice thing here is that this denominator is fairly straightforward to factor. This is going to become x squared plus x plus 1, and then in the denominator, this just becomes x plus 3 cubed. So there we go. But the problem here is that this is a repeated linear factor. When you are dealing with repeated linear factors, what you have to do is you have to make a fraction for the factor by itself, and then you have to make another fraction for each power of the factor going all the way up to its full multiplicity. So in this case, the factor is cubed, so I need to do a b over x plus 3 squared and a c over x plus 3 cubed. If this were to the fourth, I would need to add a fourth term like this, and so on. So for each time the factor appears, you get a separate fraction, and you do powers going from 1 up to however many you have. If this were just squared, we would have stopped here with the x plus 3 squared. If we had other linear factors on here, we do exactly the same thing. We would just continue, like we would then put the other factors in here as regular fractions. Okay, so this is the only difference. When you have the factor repeated, you get more fractions out of it. Now, the problem with this is that it does make calculating A, B, and C a little bit harder. Why is it so much harder? Well, not so much harder, but why is it harder? Because I can no longer just calculate things by plugging in something to get rid of these factors. Because what am I going to end up with here? I'm going to have x squared plus x plus 1 is equal to a times x plus 3 squared plus b times x plus 3 plus c. So the problem is I can't really just plug in -3. I mean, I can. That deals with the situation and gives me c. But after that, I'm going to have to be a bit more clever. So I can immediately see here that c is going to have to be equal to 1. If I plug in -3, that leaves me with just the c, which in this case has to be equal to 1. But after that, I need to be more clever in how I figure these things out. And in order to do that, I really will just need to set up a system of equations. So let's look at how we do that. We're going to have x squared plus x plus 1 is equal to a times x plus 3 squared plus b times x plus 3 plus 1. Now, my 1's cancel. This gives me x squared plus x is equal to ax squared plus, why am I confused now? 6xa plus 9a. And then we're going to have plus bx plus 3b. And there's a few different things that we can say here. So one of the things that I can say immediately is that a is going to have to be equal to 1 here. Why? Because the only coefficient of x squared is a, and on the left the coefficient is 1, so those must be equal to each other. Now, I have a bit of a problem here because I also have that 6a plus b must be equal to 1. But then sorry, give me just a second here. I know what's been confusing me. Let's back up a moment. I did this incorrectly at the start. Let me go back to the original problem here and fix this for you. I'm not going to re-record this video, so my apologies to those of you watching it. We're going to just fix this from here. We were trying to do the integral of x squared plus, and you guys have probably noticed what went wrong, because it went wrong right at the very beginning. We had x cubed plus 3x squared plus 3x plus 1 dx. The problem was this actually factors into x plus 1 cubed, not x plus 3 cubed. So what we really want to do here is we want to do x squared plus x plus 1 over x plus 1 cubed. This should equal a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. There we go. That is where I was getting myself all confused with why this wasn't working out the way I thought it should. So now what we can do is we can say x squared plus x plus 1 is equal to a times x plus 1 squared plus b times x plus 1 plus c. Once again, we get that c must be equal to 1. And then we can go back and we can say, well, this means x squared plus x plus 1 has to be equal to ax squared plus 2ax plus a plus bx plus b plus 1. And this means that, once again, the 1's cancel, and I get that a has to be equal to 1. Now, the problem is that I get two equations at this point. 2a plus b has to be equal to 1, and also a plus b has to be equal to 0. Fortunately, these two can be satisfied at the same time. So what you'll notice here, the problem is that I've got 3 equations for 2 unknowns. This is what's known as an overdetermined system. Fortunately, it turns out to be consistent, and that's because of the fact that we've got these repeated factors. So if you want to go into the details of all this, and it's quite interesting, but from an algebra perspective, the theory of algebraic equations, you can work out why all this stuff turns out the way it does. For now, let's just use the fact that b is equal to -1. That means that we can re-express our original problem as the integral of 1 over x plus 1 plus -1, so let's just make that minus 1 over x plus 1 squared, and then we have plus 1 over x plus 1 cubed. Well, now this is a very easy problem to do because we just do a u substitution with u equal to x plus 1 and we're done. And in other situations, you may have other types of things that you have to do, but having these extra repeated factors, it doesn't really do that much to you. You just end up having to put in extra fractions like this. So there we go. Again, my apologies for that momentary lapse with my factoring, but as you can see, it's easy enough to make those kinds of mistakes. Just be careful about them so you don't make those kinds of mistakes when you're doing these problems. And if you do make a mistake like that, it's okay. Just, it's a reminder to be more careful, okay? So don't be afraid of screwing things up like that. It's never a bad thing to make a mistake unless you don't realize you make the mistake and fix it. I mean, you want to obviously do things correctly. It's better if you just do them correctly, but it's okay to make mistakes and then have to go back and fix them. Just when it seems like things aren't working out the way that you expect them to, think about whether or not you've made a mistake and things like that. Now, there is one more thing that we're going to have to deal with, and I'm not going to deal with it in this lecture. I'm going to put it off to the next lecture, but I do want to mention what it is so that you know where we're going with this. Let me consider, what if I had to do partial fractions on something like the integral of 3x minus 4 divided by x plus 2 times x squared plus 4. Well, now I have a problem because this does not factor into linear factors. So that's going to give me a bit of an issue. So we'll have to see next time what you can do with that. There is a trick for still doing this. However, I do want to just point out, and this is the last thing I'll say in this lecture, if you allow complex numbers, all polynomials factor into linear factors. So, for instance, in this case, x squared plus 4, this is actually x plus 2i times x minus 2i. So this would be the integral of 3x minus 4 divided by x plus 2 times x plus 2i times x minus 2i. And I'll put my dx up there because I've run out of space. And you can do partial fractions with complex numbers exactly as you would do the problems as we've been doing them. So if you allow yourself to do complex numbers, then all I said today about doing partial fractions is all you ever need to know. You can always factor your polynomial into linear factors with complex numbers, and then you can do your integral. And it turns out doing integrals with complex numbers is not really any different than doing them, at least doing antiderivatives with complex numbers is no different than doing them with real numbers. So there's no problems there. However, what if you want to stick with real numbers? Well, next time we will see what we can do if we want to stick with real numbers and deal with polynomials that don't factor. Because remember, with real numbers, we can only factor polynomials into quadratics. Sometimes we can factor them into linear factors, but we know we can break any polynomial with real coefficients into linear and quadratic factors, but we might be stuck with some quadratic factors. When you're stuck with quadratic factors, you can still do partial fractions, but it does become a bit trickier. So that's what we will deal with in the next lecture.